Assalamu alaikum, guys. So let's start our new lecture, vestigial sideband modulation. Vestigial sideband modulation. Okay, in our previous lecture, we have seen that when we do single sideband modulation, due to the non-ideal or practical nature of the filter, there is a small portion of the signal that is actually included with the sidebands. Means if it is a LSB, then a small portion from the upper sideband actually is included because of this transition nature. This is of this transition band of the practical LSB, a practical low pass filter. Okay, so this portion is vestigial. Vestigial means portion, a small portion. So a small portion of the frequency actually added compared to the ideal low pass filter. That modulation, scenario actually gives us a new idea of modulation technique. Is called vestigial sideband modulation. Okay. Okay. So let me check if, because in our previous example, we actually, I have give you the example of a LSB generation, lower sideband generation, not the upper sideband generation. Actually, these are the same mechanism, that either in lower or upper. Let us start giving the example of a upper sideband generation example, so that I can give you, like, continue this portion, right? So we have both the double sideband suppress carrier. Then we use a high pass filter. From the side pass filter, only higher portion of the frequencies will be filtered through this mechanism. So you get the upper sideband generation. Okay, so let's start from this example, and we'll continue to the vestigial sideband signal modulation technique. Okay, so let me draw this previous example. Okay, so in our previous example, in upper sideband, in upper sideband mechanism, what happened in our upper sideband mechanism is, so we have a FC and minus FC. So we have upper portion of the signal, where actually these are actually the other part in DSB double sideband, suppress carrier. This is actually upper sideband. These are the, like, upper sideband modulation, and it is actually passed through a practical. It is actually passed through a practical high pass filter. So this actually upper sideband, and this is a practical high pass filter. The previous example for practical low pass filter, we have seen this example, seen the scenario in previous lecture. So let's see by using a high pass practical high pass filter, what it actually happens. Okay. So in ideally practical high pass filter, because of this practical nature, so let me draw this portion again. Sorry, this portion again. So because of this practical nature, because of this practical in practical, so in ideal high pass filter, this will be the so in practical high pass in ideal high pass filter, this would be the response of this high pass filter. Okay, this would be the response of the high pass filter if it's a ideal. But because of the practical nature, this will not happen. Okay, so how it will happen? It will happen that this high pass filter will have a, for example, this is plus fc, this is minus fc. So in plus fc, so practically it will be like this. So practically it will be like this. So a practical high pass filter will look like this. Here, this portion or this portion, this is actually a transition band. So these bands are called transition band. These are called transition band. Transition band. Transition of what? Transition from stop band to pass band. These are this portion are the pass band, and these portions are actually stop band. Stop band. That's why in between is called a transition band. Okay. Okay. Now, for because of this practicality, how the upper upper sideband would be look like. For example, the upper sideband would be like this. So this will be the upper part, but here, because of this transition start at this point, it will be like this. It will be like this. So it will be at FC. Let's see, where is our FC? Okay. Let me draw. It was not very good one. Let me try it again. Let me try it again. So this is actually our so this is also this one. So this is actually our. So see here, this portion is not included, but this portion got included in the filter. So same thing here. This portion didn't included, but this portion got included from the additional part. Okay. Okay. So here should be the FC, or here should be FC. So the excess amount we can. So this is actually FC plus FM. So here, because of this extra portion, this one is called vestigial. It contains vestige of lower sideband. Actually, this portion below FC, this portion actually from the lower sidebands. It comes from the lower sideband, right? Because we know here, if I mimic this part, then actually this part is lower sideband. Okay, this portion is the lower sideband. So it actually contains a small portion from the lower sideband. So this vestige means portion. So from there we find where this name terminology comes as a vestigious sideband modulation, or vestigious sideband modulation comes from this, because of the use of this extra portion, of because of the practicality of the high pass filter. In our previous case, it was a low pass filter, but in this case, this is a high pass filter. Okay, or this is a non-ideal, you can say. Now you see this portion extra, we can call it FV, vestige portion of the signal. So what is the bandwidth? So the bandwidth of of this signal, becomes what? Usually it is actually FC to this part plus, means actually this is actually FM plus this FV part plus this FV part. So this is the bandwidth. You see, this FV, this FV actually bandwidth of vestige. This is actually the bandwidth of vestige, or the additional part, or a small portion of the part. Now, what we can see that the increasing, so how the spectral efficiency varies between these three difference mechanisms. So spectral, so our spectral, if you compare the spectral efficiency of different mechanism. First one, we had double sideband suppressed carrier, which had actually how much? Twice FM was its bandwidth. Now it has higher bandwidth than what? It has higher bandwidth of any of the single sideband SSB, right? Which needs a bandwidth of FM. We have seen in our previous example. But where this vestige remains, it actually the vestige sideband actually in between, because it needs a FM plus a small portion of the bandwidth is required. A small portion, this portion. So its spectral efficiency is in between the single sideband and double sideband. It needs an additional bandwidth because of the practical low pass or high pass filter. Okay. So, but why it is desirable? Why vestigial sideband? So vestigial sideband modulation, actually this scheme or modulation scheme, this modulation scheme is in complexity is actually better, because complexity is actually lower complexity, so it has a lower complexity in implementation, because it is implemented by practical low pass filter. If you want to have an ideal like cutoff frequency like an ideal low pass filter, it would be very, very, like if you want to have a cutoff frequency like sharp cutoff frequency, then the implementation would be very, very complex. So this nullify, or is actually avoid that complexity compared to the SSB single sideband. In our cases, actually, in this example, we used upper sideband actually, right? Upper sideband as a SSB. It can be also lower sideband, same thing, because it do not need ideal filter. Requirements of ideal filters is very high. So now we have to find out what are the properties of this, because now the low pass high pass filter in our cases, they are practical. We can say that is a practical VSB, vestigial filter. So what are the properties of this? So What are the properties of vestigial sideband filter? What are the properties? What condition it should follow so that it works? The practical high pass filter or low pass filter works as a vestigious filter, or we can consider it as a vestigious filter. Okay, so what are the properties? So for that, we will actually see now what are the properties are required for that one. For our cases, these are actually this one. This one is actually a, if I redraw this filter here in a smaller size, then this is FC, like FC minus FC. So this is actually a practical high pass filter. High pass filter actually is look like. So actually the requirement for vestigial filter is actually the requirement for this high pass filter. So this is actually the vestigial filter for our cases if it's a high pass filter. Okay. So now we will actually look into the matter what are the properties this filter should have. Okay. So now if we see the mechanism. Okay. So our signal has, for example, we have a signal. Now how the modulation and demodulation actually works for these cases. Say we have a signal empty, message signal empty. Now this signal actually up converted by a carrier signal cos 2 pi fct, which actually pass through a, because this is xt, xt becomes, this xt is actually double sideband. So it actually pass through a practical high pass filter. So practical high pass filter having a response ht, impulse response ht, and there what we got the signal xt, got complex conjugate with this response of this filter ht. Okay, actually what it happens is that when you pass through a signal through a low pass filter, is actually convoluted through this impulse response of this filter. Okay, so this is actually a convolution. Okay, so what will happen to the frequency domain response of this convoluted? So what is the response? So what is the response of this, which is actually nothing but the so if we do the Fourier transform of this output signal, so xt, so it's actually the Fourier transform of this xt, right? Xt convoluted of ht, which is nothing but what is xt? Xt is nothing but mt cos twice pi. So it's actually Fourier transform of mt cos 2 pi fct, this signal convoluted. So convolution in Fourier transform is actually multiplication. So it's a multiplication of, and ht becomes capital of hf. Okay, and we know that Fourier transform of this mt is nothing but half of, we solved this earlier, so I'm not repeating this solution, f minus fc plus half of m plus mf plus fc, which will be multiplied by HF. Right? So what is the spectrum, output spectrum here? So like here, output spectrum here. So the output spectrum in the modulator, this output of this modulator is nothing but, say, output spectrum is, say, x, value x, which is actually nothing but this one, this multiplication. So that is the output, which is actually half of mf minus fc hf plus half of f minus fc hf. Okay. So this is actually our this is actually x. So we called it x VSB. Here is vestigial. So this is actually VSB. Here actually is the x vestigial sideband. Here actually we receive this signal at here actually. This is actually here at the output of the practical high pass filter. Okay. Okay. So this is the modulated signal. So this is actually we can write it. This is actually VSB modulated signal. Now we know the modulated signal, which will be transmitted and will received by at the receiver. Okay, so let's see what happened at the receiver. So this is the output spectrum of transmitter, of a transmitter, or modulated output modulated spectrum. You can say modulated spectrum at the transmitter. So this happens at the transmitter. What happens to the receiver then? What happened to the receiver? So when we receive the signal, say this receive signal is RT. So at the receiver, we receive the signal RT. Okay. If we do the Fourier transform, that will be like R of F. So what is actually our signal receive? So whenever we receive the signal X, this X signal X. So we signal X VSB. We receive the signal X VSB. Okay. Whenever we receive this signal, sorry, this is actually in frequency domain, so it's okay. X, which is actually in time domain signal, we receive this signal, we actually multiplied by the carrier again to down convert the signal. Previously it was up converted, now it will be down converted. So cos 2 pi fct. Once we do that, we actually got a RT signal, which is actually and then we got this output of the demodulator. This is a demodulator. So the output of demodulator. So this is the modulator section. Previously, where we modulated? Yeah, this is a modulator. This is actually our modulator. This figure is a modulator. VSB modulator. And this figure is actually demodulator. This is actually our demodulator. VSB demodulator. Okay, good. So what we have at the output, so we have our signal RT is nothing but XT modulated by demodulated by cos 2 pi FC T, right? Okay, so if we do the Fourier transform, then RT becomes RT, R of F, which is actually X. So this, we already know the solution of this one because we already solved it many times. So it's half of X F minus FC plus half of X F plus FC. I'm not deriving this equation again and again. So we know the solution from the previous one. You see, this is actually X. So what is this X? This is actually this X VSB. So X actually VSB. This X also a VSB signal that was initially transmitted. So what we can write? So we can write at the receiver of the spectrum of the demodulator. So spectrum of the demodulator. So we can write the, okay, so we can write at the spectrum of the demodulator. So we can write the spectrum of the output. So we can write, what is the RF, the spectrum of the output of the demodulator. So this is actually the spectrum of the, so this is actually spectrum of output of the demodulator, which is actually here, this one, output of the demodulator, which is actually RF. So let is go, this is the spectrum. This is the spectrum. This is the spectrum. Let us write it. Okay, so what is this RF? R of F, R of F. Now let us, we know this X, which we will actually replace, we will use this equation X. So X will be replaced by this one. So what we find if X is replaced by this one? So what we find is, half. That is half. So X F minus FC. So if X F minus FC will be this, this part will be modified. Okay. So from here, half M F minus FC will be replaced by this is actually XF. XF. Then it will be easier to understand. So we can find half of M F minus twice FC plus half of M F multiplied by the HF, HF minus FC. Because this is XF, so XF will be replaced by XF minus FC in this equation. All the F will be F minus FC. So that's why F becomes F minus FC. So 2 minus and minus FC becomes twice FC here. You see, this is how we got it. Okay. So this is the one portion. And what is the other portion? So this is for this part only. Like this part is actually this part plus half of, we need to close the bracket, again half of half M F plus half of M F plus twice FC multiplied by the H F minus F. This was minus, so it will be plus FC, which is actually closing this equation. Okay, so we actually write the whole one. So half becomes 1 by 4, half into half. So M F minus twice FC H F minus FC plus 1 by 4 M F H F minus FC plus 1 by 4 mf h f plus fc plus 1 by 4 mf plus twice fc h f plus fc. Okay, so we have 4 terms here. Okay, so we can see that this twice fc and this twice fc, these two components, these two, they are actually in these two, this one and this one. You see, their center frequency is in twice fc, so they are corresponds to the, these are the two component corresponds to, so these two component and corresponds to twice fc at frequency, right? If we see in spectrum, so this is actually, you see, this is actually our fc, so it will be somewhere here, like higher frequency twice fc, and also there in this region minus twice fc. So this, they are actually too far, and that portion can be filtered out. Okay, this can be eliminated by a low pass filter. So this portion can be eliminated by a low pass filter. So this portion can be eliminated, by low pass filter. Okay, they are passed through the low pass filter. We don't need this two of the portion. Now what will be the output? So the output of this low pass, after passing it low pass filter, what will have? The output is 0%. Now we already gave it a name, RF, so let's give another name, R prime or R tilde F frequency. Okay, so what we have actually 1 by 4, this 2 remains stuff. Okay, 1 by 4 m f h f minus fc plus 1 by 4 m f h f plus fc. These two portion actually we have now. Now our aim is, so okay, a little bit modification. Just write it 1 by 4 mf h f minus fc plus h f plus fc. Our aim is actually, what is our aim? Our aim is to make this portion equal to 1, filter response to 1, so that if this becomes 1, then our 1 by 4 of mf, or this will be actually our, or we actually convert it to our message signal, so this will be our mt. Okay, so this way we can actually recover original message mt. So this is the way, right? So what was the main assumption here? This is actually main assumption. We like to have it, this response of this filter as 1. Which filter? So that is actually the this VSB filter. We are looking for the requirements or properties of this filter. What is the requirement? Requirement is this. If we can make it this VSB filter response is 1, then we can recover our message signal. Okay, so That's actually our requirement. So what our requirement comes as a H F minus FC plus H F plus FC equal to 1. We like to have it. If we can have this one, that will actually satisfy our non-ideal VSB filter. So our actually practical VSB filter properties, say, or it should be satisfied. So this is actually the required properties. So our VSB filter should satisfy these properties. Okay. So now we already know what is the properties of the VSB. Now this one, how it actually look like what it looks like. Now you see in our low pass filter, sorry, this is a high pass filter. So what was our high pass filter response so this was actually our practical response, ideal response of this. Sorry, this is a practical response of this high pass filter, right? So let me draw this one again. So this is actually a response. Initially this was the this was our okay. So this was our response here. So this was the center, this was our FC, this was minus FC. So this is actually FC, this is minus FC. So if see here, our filter response become like this, isn't it? Like this. So filter response become like this. Which is actually HF. Now you see it becomes HF minus FC and HF plus FC. Means actually what will happen here? What will happen here? This response shifted. So this response shifted. So this response become, so this response shifted to origin because of this HF minus FC. So it's actually shifted here, or this is actually also shifted by this one. Okay, so if I draw it here, so it will be in here. It will be like this. It will be like this. Same thing. Same thing. The other portion will also like this. It will also be like this. Because of this one. So this will be shifted like this, and this will be shifted like this. It was at FC, but it will because of this FC FC minus FC, this one. So you see this term will shift this one to this, and this term will shift this shift this to this. Understand? So we will actually, if we combine these two responses like this, if we combine these two response, then we will actually got this response as a unit response 1. If I combine this one, which is actually this one, so this will be our response. Okay. So now we can see here, for example, one of the example here. So let me make it looks nice. So this one. Okay, so let me draw it again. So this one will be response will be look like this. This is our This is actually our high pass filter response, right? This is actually FC, and this portion to this portion. So this one actually what? This actually FC minus say del F, and this portion will be FC plus del F. Okay, so what will be, and the slope, what will be this slope? This slope will be nothing but 1 by twice del F. Okay, so the function of this filter will be F minus FC plus del F. Okay, so FC is in the midpoint. So we can see that this VSB filter is symmetric about FC. That is, FC minus del F is the point. Let us say that FC plus del F is this point. Okay, so this is the symmetry about this point, midpoint FC, and the linearity is increases. Here we can see this is a linear. This is a linear slope. So the linearity increase from this area to this point means the slope is actually, the linear slope is this one, and FC is the midpoint. Okay. Okay. Now, when we have this, so when we have this, so when we have this one, when we have actually this one, what is the, so we finally found, by combining these two, we found finally is this one. Okay, what is the properties here? So the practical high pass filter which satisfies VSB properties. So what is the properties here? We can see the properties as HF is so we find the properties as this one. So what is the filter properties? We can actually summarize the filter properties from here. This one. Let me write this filter properties here. So we can see that, okay, this filter properties has a like zero value. Okay, zero value where? And the frequency F is F minus this one. So F is less than F minus del F, means beyond this value, its value is this is zero. This is zero, and it has a value of 1. Value of okay. You see here three portion happens. This everywhere here is 0. This where has a filter response of like this one, and here the filter response is 1. Is 1, right? So 0 and 1, we know what is 1. 1 is when it's beyond this value. This value is beyond, right? So which will be actually F is greater than is FC plus del F. What is in between? In between, we know this is the response. So in between, this is the response is 1 by twice del F minus FC plus del F. Okay, so our practical filter to satisfy the VSB property should have these properties. So it has 3 regions. Region 1, region 0 means like anywhere, here, no response. Other is 1, like anywhere beyond this region is 1, 1, 1, 1. In between is this value. In between is this value. This is the response. That's actually we found. Okay. So let me clear it so that it looks a little bit nicer. Okay. So now you know that this is actually the response of this VSB filter. So by using a practical high pass filter or low pass filter instead of ideal, if it's ideal, that we use it in a SSB, but if it's not ideal, then vestigial portion remains, then we call it vestigial modulation or demodulation. Then that ideal filter becomes a practical filter, and that practical filter is a VSB filter which should have these properties. So this is the end of this lecture. Thank you. Assalamu alaikum.